We started a few minutes late, so we might be extending the session a little bit, but I promise to stay on time and to give everybody a chance to ask questions. Our next speaker is Thomas Piechota. Dr. Tom Piechota is the Vice President for Research and Professor of Environmental Science and Policy at Chapman University in California. He received his bachelor's degree in civil engineering from Northern Arizona University and his master's and PhD in civil and environmental engineering from UCLA. He has been recognized for his efforts in teaching, research, and administration. Tom has received National Science Foundation Career Award. Career is one of the most prestigious awards that you can get from the National Science Foundation. And he also served as a co-PI on a $20 million National Science Foundation studies on climate change impacts in Nevada. Tom today is going to be sharing some of his thoughts about climate impacts, as well as he's going to show us the case study of the Colorado River. And without further ado, let me bring Tom to the podium to talk about water supply forecasting innovation using some climate indicators. Tom.
Thank you, Hisham, and thank you to the organizers of Cairo Water Week. It's been really fun so far, and thank you, Professor Al-Askari, for this interesting session. So as he said, what I want to talk about today is some work that we've done over the years. Actually, I'm presenting some published work that we've done over the years on the issue around water supply forecasting using climate indicators. It's always interesting to see how can we look out into the future and make forecast outlooks of water supply, stream flow, or different hydrologic forecasts based on climate. And this is work, like I said, that we've published over the last 20 years probably, but focusing more in the last 10 years of work that we've done. Primarily focused in the US, but it has the way these are all data-driven models, so it really has broader applications. It's work that we've done in Australia also. So, framing the problem, like I said, really it's a basic problem that I think everyone would like to be able to solve for basins that they work in terms of looking out over 1 to 12 months in advance. How can you provide outlooks? Sometimes we call them outlooks because we're always hesitant to say this is an official forecast, and sometimes you couch that in terms of a probabilistic forecast. It's not necessarily one single number, but outlooks of water supply or hydrologic variables, those may vary. Sometimes they may be a stream flow forecast. Sometimes it may be a drought indicator like a soil moisture or Palmer drought index. In regions where I live in the US, snowpack is part of that also because it's a driver of stream flow. But many times if you're looking that far out in advance, you need something to be able to allow you to look that far out in advance. So climate is part of that. Climate indicators are part of that. And typical climate indicators that are part of that are some of our usual actors are the ENSO is one that's been studied for many parts of the world, and I'll show that. Other longer term ones like the Pacific Decadal Oscillation, Atlantic Monthly Oscillation. And then I'll present some work where we don't necessarily precondition it off of indices, but we look at kind of the oceans and how the oceans drive climate in particular regions also. So that's the basic problem that we're looking at and how we use climate variables in data-driven systems. Many times it can, and the methods around that may vary. Here we'll present some in terms of using machine learning to kind of drive that, and data-driven systems to kind of produce kind of outlooks and predictions on that case. So as I said, these are the usual actors in terms of climate variables. ENSO and PDO. ENSO, as you see there, El Nino Sudden Oscillation operates at kind of a 2 to 7 year time frame. So it goes from one phase to another phase over that time frame. Pacific Decadal Oscillation, it's a longer one. It's more of a decadal time frame. So these are climate variables that force climate conditions in different regions, and and sometimes are useful in terms of looking at sustained droughts in certain regions also, because drought kind of operates at that longer type of timescales also. Same thing with Atlantic multi-decadal oscillation. You can just see by looking at the graph there over on the right, it's something that goes into a phase and stays in that phase in a long time frame also. So sometimes by looking at these types of climate indicators, it gives you a sense and an ability to kind of see, are you shifting into a certain type of climate regime that will allow you to kind of look and see, will that help you with streamflow outlooks into the future also. The other one that I said was sometimes if those types of climate indicators aren't necessarily strong in a particular region, sometimes we go back and look at the fundamentals of how do sea surface temperatures, which drive the climate, how do those influence the hydrology of a certain region also. And what I'm showing here is just some work that we've done in the US here, where we took on the left side there all the Pacific Ocean sea surface temperatures, and looked on the right side there of all the streamflow stations in the United States. And it's hard to see on there, but we map those out and we do something called singular value decomposition, where you look at two fields, and by pulling out the major variability in those two fields, think of it as the first component in that. You see that the highlighted regions of the sea surface temperature there, the hot spot there in the orange, and the blue being the positive one, and the orange being the negative one, how that relates to streamflow in the US there. So what you're basically pulling out of that is those being the drivers of climate or of hydrology in the United States, that being one of the major drivers of that also. I'll show here in a minute how you can narrow it down to specific regions in the US also to really start to help you in terms of streamflow forecasting also, but at a large macro scale, this allows you to look at some of those major drivers. We did a similar analysis for that for the Atlantic Ocean sea surface temperatures, where you look at Atlantic Ocean sea surface temperatures on the left there and streamflow on the right for the US, and you see some of the major drivers there in terms of the major drivers of sea surface temperatures in the Atlantic and how that influences certain streamflow stations in the US. And not too surprising, many of those are in the eastern side of the US. It doesn't necessarily impact much of the western US streamflow stations. Going back to El Nino, when you look at a climate indicator like El Nino, it has broad impacts, and many of you may live in some of these regions during an El Nino winter, and it can vary a lot too, which is interesting because you look at regions like South America, you have different colors there. In the bottom portion of South America, where it's green, that's cool and wet. But when you go up to up further in South America there, it's dry, it's warm and dry. So El Nino isn't necessarily something that it drives the climate. The same impacts are the same throughout the world. They vary a lot depending on where you are. Could be warm and dry in some, warm and wet in some regions. That being the El Nino region there in the central part of the Pacific. But then when you go into the southeast U.S., it's wet and cool. So the impacts are broad, but they vary also. That's the important part of doing an analysis and looking to see where is it in the U.S. that you're working. So I want to focus now, finish my talk on work that we've done over the years in the Colorado River Basin, and finish with a mapping of that with the Nile River Basin, because there's some interesting comparisons that you can make. The Colorado River Basin, it's a large river basin for the western US. We have units where we use million acre feet. It's a funny unit that they use in the US, but I made my conversions there to kilometers cubed. But the interesting part in the numbers that I show there is the allocations. 20.3 kilometers cubed allocated, and then when you go down there, you look, 18.3 average flow. So if you just do the math on that, it's an over-allocated river. So they have their own challenges with management of the river there also. I'll show in a graph here where they've been able to get through that over the years here, but they're pointing it to now where they have to work together in states in terms of managing a river like that. So it's certainly a river where they have their management challenges. They have their own needs for predictions like this also to help them manage that. One thing that gets them through sustained drought periods is the bottom number there. The 74.3 kilometers cubed of storage, that's a lot of storage. That's 4 years of storage in a river like that. So there's some really large dams there, like Hoover Dam. Many people have heard of Hoover Dam. And then there's another one, Glen Canyon Dam, which form 2 large reservoirs, Lake Mead and there's another one behind Glen Canyon Dam also, which create a huge amount of storage and allow the region to get through long sustained droughts. So this is a graph that is interesting to show how over the years the region, the water supply, that being really the water in the river, you know, I showed you the number there of what they've known it to be, but their water use in the region just until recently have those 2 lines crossed each other. So now they're to this point where they have to be able to manage to really what the true water supply there is. So now they're having to work together as states and manage that appropriate water supply. The interesting thing on that, on the red line there is if you look in the last, say, 10 years there, it's actually a drop in the water use, and drop in the water use because of the things that are probably talked about in today's panel in conservation strategies, both in the agricultural sector and then in the urban sector also. And I like to show my little picture there of me at a treatment plant where they do something in the US. They don't like to broadly advertise this, but it's called Toilet to Tap. Toilet to Tap is actually a program where it's a reuse program where in fact, it's not necessarily toilet to tap, but what they're doing is they're taking wastewater, treating it to a really high level, injecting it back into the ground, and then pumping it back into the ground for water use. And it's really an effective program. And they're doing it in urban areas in Southern California now. But it allows them to kind of drive down the water use in areas now. And this is just one of the major lakes that we have there, and just to show how that lake has really changed over the years because of the changing climates, but also because of the water use in that region. Also Lake Mead, the one behind Lake Hoover Dam. The other interesting thing that you can see on that in the beginning of the graph is the filling of that lake, how long it took to fill a lake like that. But we're at historically low levels there, and something that they have to manage. You know, the lake's about 39% full right now. So let me get to some of the analysis that we've done in terms of improving streamflow forecasts using climate indicators. For the Colorado River Basin, what we did was looking at this analysis of how do these climate indicators impact the river flows there. And starting from the left there, when we look at that river basin, you can look at the ENSO indicator and how the box plots shift up and down. So during an El Nino event, more stream flow. During an La Nina events, less stream flow. During the Pacific Decadal Oscillation, you can see the different phases there, how they shift. The AMO doesn't really have as much of an impact. what I want to emphasize in here is also one of the interesting thing that we did, and I circled it in red there. When you couple the two together, El Nino and Pacific Decadal Oscillation, because they operate at different scales, you get sometimes enhancement of the impacts. So for instance, during El Nino events and you have the PDO warm phase, you get an enhancement of the impacts of in this particular region. Or during a La Nina PDO cold phase, you get further negative impacts in that region also. So sometimes it's important not necessarily just to look at these indicators by themselves, but also the coupling of those indicators also. And then, as I said, we've done a lot of work on looking just straight how do sea surface temperatures impact climates in the regions. And this is some work that we did in terms of for stream flow stations within the Colorado River Basin, how those drove, how sea surface temperatures drove specific stream flow stations within the Colorado River Basins, and really started to narrow down a specific region within the Pacific Ocean and how that's a real driver within the Colorado River Basin. And out to 1 year in advance in what we were looking at for some studies here. So getting even further down and how this gets into kind of the applications of making a streamflow outlook and what the skill might be with something like that, we took 6 stations within the upper Colorado River Basin, applied some of these climate indicators and sea surface temperature zone that we identified here, used machine learning with that. And on the right there, you see some of the skill associated with that. And what I want to highlight with this is each one of those bars is a specific station, streamflow station. If you're above the red line, that means you're basically beating climatology. If you can't beat climatology, then you're better off just average or estimating the average. So in a lot of these instances, by coupling together a climate indicator with sea surface temperatures, we were able to beat climatology. But in some instances, you're not. You're better off just, when you're going 1 year out in advance, you're better off just estimating kind of what the average would be. But in several instances there, by coupling a climate indicator with sea surface temperature as an indicator, you could get a skill, a forecast with some skill in it. And in the bottom there, just demonstrating that the variability in these forecasts represents the variability that you would see in the observed streamflow data also. So these aren't perfect. They have a lot of variability in those, but there is some skill depending on how you look at those and depending on what stations also. What they look like when you realize these from a water manager standpoint is this is what a water manager might take from something like that, and how they might use it as a probabilistic forecast and project that out over time, over 1 year, in terms of probabilities, and how they might map that onto different zones in the reservoir too, in terms of whether they might be hitting shortage conditions in a zone also. And I work pretty closely with the Bureau of Reclamation in our case, who's our water authority, in looking at something like that. And then we've done similar analysis like this for using other climate indicators. Soil moisture is in this case a hydrologic indicator that we've looked at, where we see similar signals in soil moisture, where in soil moisture we see the Pacific Decadal Oscillation come out. Soil moisture is has a much longer resonance in it, and it's not something that changes as quickly, so you see things like the Pacific Decadal Oscillation signal in something like that. So I will just finish with some thoughts on commonalities that we see between work that I've done with Colorado River Basin and mapping on things like the Nile River Basin. there's a lot of commonality between those two basins, both in terms of the geography, the growth patterns that you've seen in those, the building of dams for the same types of purposes, the shifts from agricultural to urban demands, so the supply nature and within those basins and other environmental concerns in those basins also. So with that, I will go ahead and finish because I want to keep us on time and look forward to any discussions that we might have. Thank you.